Thank you, Mr. Chairman. I appreciate the introduction. It was very mysterious. Yeah, I like this. Good afternoon, everyone. Maybe I didn't use the right term. I'll try my Portuguese. Bom dia. I try. I've been in Italy for 2.5 months or a month and a half, and I'm doing just now buongiorno. So thank you. So my non-English speaking is poor, to say the least. So let's try at least one more time so I know everyone's awake. Good afternoon. Yeah, perfect. So at least a few people are awake. So you can see the title of the presentation, and when I looked at the program, I saw I was talking in cost-effective pavements using recycled crumb rubber, which is somewhat of an odd location for this talk, which is fine. I like talking in crumb rubber sections. It's very nice. But I thought, as I saw that it might be worth spending at least a couple of minutes to explain what this work and what my presentation is really about to you. And so I thought about how to do that, and I decided that I would use a story to do this. And I'm going to use a story from Aesop, the Greek storyteller, to kind of convey what the research that I'm going to present is fundamentally about, how it is related to this conference, and tangentially how it is related to crumb rubber. And the story that I want to tell, I'm going to tell it in a very brief form, is the story about two plants, a tree, in fact an oak tree if you like, and grass. And the story goes something like this. We have an oak tree that is strong, it is tall, has very deep roots, and it is able to withstand things that come at it. And it stands up to this for years and years until one day something happens that has never happened before, a stronger wind, a wind that is stronger than anything it has seen before. It is different from its past, causes the oak tree to fall. And in the story, Aesop goes on to say that there's a conversation that now occurs between this tree and the grass that it falls to, which goes something to the effect of the grass asking the tree, "You're so strong, you're so big, you have been able to withstand things, why are you now falling down?" And the moral of the story becomes that the tree was inflexible to a change that it had not encountered in its past. Now, how do we translate that to pavements, and then how does it translate to this presentation? Well, fundamentally, what I'm going to be talking about is an assessment that we have done using model predictions from climatologists. I'm not a climatologist. We simply use their outputs to look at how these threats can potentially affect pavements. It's relevant because, of course, we design our pavements to withstand multiple decades of time over which changes that were unintentional or unexpected may manifest into effects to these infrastructure. And that's fundamentally what this talk is going to be about, is some analysis to examine this effect. So I'm going to talk about climate change, and I say climate change and its threat to infrastructure. What I should say is climate's effect on infrastructure, and it is a potential to impact the long-term performance. We did some analysis looking at the U.S. pavement network, the contiguous U.S., and I'll talk about how we did that using binder metrics. We also used a structural analysis to look at this phenomenon and this effect, and I'll talk about what we found from that, and then wrap up with some conclusions and try to tie that back to how it's related to crumb rubber and newer or modified systems, pavement systems. So it's been said that pavements are among the most difficult pieces of infrastructure to engineer, largely because they are continually exposed to the environment. And this environmental effect can manifest in many different ways. We can generally and broadly characterize these effects into heat-related phenomenon and moisture-related phenomenon. Of course, we all know that they're not easily separated in this way, but we can, for the purposes of a discussion, look at that. And when we look at heat-related phenomena, we start to think about potential for oxidation. Oxidation is a chemical reaction driven by temperature, and so heat affects how that reaction occurs and its long-term effect. We can also see that heat affects pavements, especially in cold climates, that will the moisture freezing and thawing, and how many times this happens and how this effect drives performance. We can also look at heat affecting performance measures that we generally understand very well, cracking and rutting and so forth, and then expansion and contraction of these materials that we have. These effects are, irrespective of climate change, these are climate's effects on pavements. On the water side, we have movements of water table, of course, affecting the soil stability underneath the bound layers. We can also think about our soil types in specific areas where we have soils that are expansive, or in the case of droughts and when weather changes, perhaps collapsible, volume-changing soils, and drainage and unbound layer deterioration as well, all of these driven by moisture phenomena. Now, if you see a diagram like this, it seems pretty straightforward. We can separate these pieces or these phenomena into different pieces. But just this morning, I found an example. This is Big Sur in California today. This is going on now. Of a landslide. Now, this particular landslide, if you can see a road heading from this side, and then a big pot of soil, and then road heading over here. So this landslide is interesting, and this location is interesting because it's a combination of phenomena, just to convey the effect. Here in this area, there were several years of drought. In the past winter and fall, there had been a significant amount of snowfall, a high volume of water. Coupled to the fact that heat has been high this season means that the snow melted rapidly, which saturated the soils, made them unstable, and led to a collapse. Also affecting this is the fact that there have been multiple wildfires in the area. So these climate effects are all interrelated. It's not as simple as separating it into bins, as I've tried to do in the first part of the slide. Now, in the rest of the talk, I'm going to talk about one particular branch of this, which is heat-related phenomenon, and the potential for cracking and rutting-related distresses. Now, when we think about heat, we have to start looking at what climatologists and experts in the field suggest or propose may happen in the future. And there are some statistics that are on the screen. Essentially, we've seen this morning, they project that temperature is going to rise, and that it will rise to the tune of 0.5 degree to 5 degrees Celsius, depending on who you believe. That number could be higher, slightly lower, but the direction is fairly consistent, at least in this body of literature that you find. Now, what a climatologist cannot do, what they can do fairly easily, and what you see in many of the graphs that you may encounter if you look into this area, are global temperatures. Temperatures at scales that are significantly larger than our infrastructure components. They honestly can only tell us what happens to the temperature. They are not experts in infrastructure as you in this room are, and they cannot expect how that may manifest. Analysis to look at this kind of falls into a couple of categories. One where climatologists pretend to know about infrastructure, and they project the temperature rise and say very vaguely this will make roads rut more. My favorite is when a climatologist refers to asphalt that it's going to melt faster. This is the kind of terminology that you may encounter. Another effect might be to look at simply temperature rise and try to correlate that, and imagine in your mind that you know where temperature rise, you know where infrastructure is, you overlap them together, and you say, where do those two intersect? That's where we're going to see the most effect. And the problem with that is, again, all of you in the room know, we do not engineer our materials the same way everywhere. The bottom image tries to convey this, and it's hard to see, and without the context, you may not understand, but let me walk you through it very briefly. Red means temperature is going to increase by a certain metric. It's actually number of days greater than 100 degrees Fahrenheit. Red means that number is higher. Yellow means that number is lower. Now, in this diagram, if you look at those systems overlaid on top of each other, you might say this area is more prone to climate change than this area, or future climate values. Now, the problem and the context that you need is that this location is about 300 meters above sea level, and this location is more like what we would say 2,000 meters, 3,000 meters above sea level. So we have this difference, right? Now, everyone in the room says the elevation is different, the temperature is different, the engineering today is different, and therefore we cannot simply lay these differences on top of each other. And it's from that perspective that we started our analysis. Now what we've done is we've looked at historical data. There's a network of climate stations across the US, so we wanted to see what did the historical data record tell us. Now this is quite relevant because in pavement engineering, we do not use this term, but we do the process of assuming that our climate is stationary. The technical term is stationarity or non-stationarity in climate. And in particular, we use a database from approximately 1965 through 1995, because as George reported, we rely on a $60 million project that just happened to end around 1995. We then added to that a series of climate projection models. Now, we use these models downscaled so that we can get to a scale that is similar to our pieces of infrastructure. 1/8 degree on this diagram essentially means that we can get the climate in 12 kilometer by 12 kilometer blocks. Imagine you break the world into a grid of 12 kilometers, and we look at those climate projections. As is standard in the area of climate projections, we used a bunch of different models. The idea being none of them are right, but collectively they tell a story, and we want to know what that story of the collective is. We did this across several weather stations. In fact, we took about 5,000 of these weather stations for the reported data. We applied basic algorithms of temperature projections to link air temperature to pavement temperature, as is standard practice. And we examined how the binder grades, as we specify in the US, might change over the course of different time periods and for different types of future scenarios. Climatologists, when they look at these different scenarios, they envision a world where we have continued to do what we've done. We have polluted and emitted and maybe had several tire fires in the meantime and produced quite a bit of carbon dioxide. And they also imagine a better world where we stop doing these things. So we have a high range and a low range, and we've done both of those. When we looked at the historical data record, we were actually quite surprised to learn something interesting. Now, all of these dots represent the climate stations for which we have a climate record going back to 1965, up until, and we happen to do the analysis, 2014. We conducted the analysis using a 1965 or 66 to 1995 data record, essentially representing state of the practice, what we do today. When I select an asphalt binder, I use a stationary data set. And then we said, what would happen if we only looked at the more recent data record, 2014 to 1985 instead? And what we ended up finding was that around 30% of the weather stations that we examined in the US were different. To me, that was a shocking number. That's a large percentage of the weather stations that we looked at. Not all of those were affected by the high temperature and the low temperature. You can see the color coordination here. Significantly more of the stations were affected at the low temperature, meaning that when we think about the distresses related to thermal cracking, they may actually be more positively affected in this more recent past than they were assumed during the superpave years. We then went on to start looking at what might happen in the future. And we broke our time scale into a few different blocks. 2010, the scale that's labeled 2010, meaning what happens if we look at the climate record from 2010 through 2040 and project what might happen to the high temperature grade. And we see there's not much change, right? At 0 to 1 degree change predominantly in the Midwest areas of the US. By 2070, sticking to the standard practice of using a stationary climate record, we see a huge difference. Now, there are practical issues. Would we even have the specification in 80 years? That's not really the point. The point is, what is the impact of ignoring the climate record that we have and ignoring the fact that we do engineer these infrastructure to a significant time period? And by 2070, we see that the impacts are quite substantial, 8 or 9 degrees difference in terms of the pavement record. We correlated this and looked at this on a regional basis. We broke the US into several sub-regions. You can see them labeled on the screen. And we compiled how reliable those projections are. Now, when we specify asphalts in the US, we do so that we have some reasonable statistical certainty of the temperatures not being exceeded. As the temperature rises, at least as projected from these models, that certainty starts to decrease. And we find that regions in the southeast, Ohio Valley, and northern regions are particularly prone to this. Now, this is simply the threat. What is the impact of the temperature? What's missing in the analysis is overlaying the extent of the network, and that's what we did next. So we took these weather stations, we identified the mileage of roadways that were associated with each of those weather stations. In the U.S., the transportation infrastructure is substantially denser on the eastern seaboard than it is in the west, which you see kind of explained in that upper map. We tied this loss in temperature grade to performance. I'll spare you the details of that. I'm sure happy to share those with you if you're interested, by looking at different types of pavements. And then based on that reduction in temperature, or reduction in performance, we wanted to look at what the impacts of that might be economically. We separated the data by, I did not clarify this, RCP 4.5 essentially is the future world where around mid-century we stop polluting as much. RCP 8.5 says we keep polluting the same amount. We get our cars bigger, right? We buy more Volkswagens. I'm sorry if anyone has a Volkswagen. Right? We keep doing the things that we do. We basically continue with our lives as they've been. And we see, of course, if we limit emissions, the models predict lower temperature, which projects fewer costs. But the impacts are not insignificant. These costs by 2070, according to this analysis, could exceed $45 billion. This is not a small amount of money. This is a major impact to our economy. We coupled this with not only life cycle cost analysis, we also looked at the life cycle assessment. We've heard several presenters talk about greenhouse gas emissions, CO2 emissions, et cetera. And we started to look at what the impact might be on those greenhouse gas emissions. Now, the numbers here, the problem with doing life cycle assessment is knowing what the numbers mean can be a little challenging. Okay, so there are 21,000 gigagrams of CO2 equivalent. Knowing what that means is challenging. But let me put it in perspective. An estimate using this same framework, the same life cycle assessment framework, looked at the city of Los Angeles in the U.S. Los Angeles, as you know, is a very large city. If you look at the amount of emissions from that analysis that were used to create the city from its inception through today, 21,000 gigagrams of CO2. So what this analysis tells us is that by ignoring this effect for our pavements, according to this analysis, we're essentially creating another Los Angeles every 30 years in the world. This is a way of framing what the analysis suggests might happen by, again, ignoring the threat. We broke that down by region, by state. We found that obviously states that have large transportation networks, this is a pain to see, and you probably don't know what the abbreviations mean, but states here, like Texas, which is a big state with a big transportation network, is expected to have a larger cost impact. But when we look at that by lane mileage, so when we think about each state's impact in terms of the size of its network today, those costs become much more coherent across each of the states and each of the regions. And we see that states in the Northeast, where we see generally lower total cost because of the density of the network and because of the nature of the network, the cost can be quite high. Again, looking at vulnerability across the U.S. We couple this with more detailed analysis. We wanted to look at structural analysis. Here we're looking at the asphalt binder grades, but we wanted to know what would happen in a case where we better simulated the future rutting or fatigue cracking. What is that impact to our transportation infrastructure? So we did another approach, very similar, where we looked at 5 specific locations. We know the pavement, we know the nature of the pavements, we have an ability to predict how those pavements will perform using under different future climate scenarios. So we chose locations that were spread across the United States, each of them exhibiting a substantially different baseline climate Generally, if you're not aware, here, Bozeman, Montana, is a very cold place. It's lots of snow, lots of ice. Phoenix, Arizona, if anyone didn't know, it's very hot and dry. And then every location has a slightly different baseline climate. We projected the impacts using structural analysis. This is a snapshot is a backdrop to say we conducted a mechanistic analysis of these pavements under future scenarios of warming and compared that to a baseline. The key is that we wanted to actually look at what is the impact in the long term on real distresses, rutting, cracking. You know, our skeptical approach was that temperature is going to rise, but the impact is 4 to 5 degrees, which may not affect pavements that much. So why do we worry about these things, aside from obviously the social responsibility we have as human beings? What we found was actually quite interesting. We obviously find that different locations, depending on the models, have different levels of expected impact. Now, this impact and what does it mean was more interesting part to us. We obviously see there's uncertainty. The diagram is essentially showing you what the impact on the rutting or the cracking is, and the band tells us how uncertain we are on those projections, which is quite large. But we can identify from this that the changes in the performance are often, as a first-order approximation, going to be tied to the increase in air temperature. What you're looking at on the left-hand side of the screen is the increase in fatigue cracking for a change in the MAAT is simply the average air temperature of that location. On the right-hand side, again, change in rutting. What's striking about this is that they suggest a relatively small change in the temperature has a proportionally larger impact on the performance. It's most obvious in the case of rutting, where we can see that 10% change in temperature results in something more like a 15 or 20% change in the rutting. Again, projected. There are discrepancies here, which is where we can start to learn some interesting things. For example, what we find, this data series here, this is for a main projected pavement. The green triangles here, the main pavement. When you look closely at the design structure, you learn that it has a relatively low traffic volume and a relatively thick pavement structure, indicating, and less sensitivity to these changes, indicating that with respect to temperature rise, which is not entirely unexpected, a thicker pavement section may actually be beneficial in a way to mitigate or remain resilient to these effects. On the other hand, if you look at rutting, you see that relationship doesn't hold, meaning that building or structurally building our way out of this relationship or this effect is not a possibility, which begets more interest in materials. We also find that there are points that lie significantly outside. Now, this one ends up being very interesting because it provides us a unique insight, which I think is important to keep in mind. I think you're probably aware of this, but you may not have explicitly thought about how temperature affects our pavements. And it becomes most obvious when you start to look at a location like this MT I-90 section and this point that's up here. What it tells us, as we look at more detailed analysis, is that we can't simply look at the mean increases in temperature. Pavements do not evolve and the distresses do not evolve uniformly over the period of their lifetime. And what we see from this is that we can reduce that discrepancy by looking at other climatological factors. In this case, how much the temperature increased in the single month of July, in the hottest part of that day of the month, might impact that performance. And what we learn from that is that in this particular point, the climate projection tells us that in that 1 month, the heat rise is going to be substantially greater. Okay, so we can learn how these climate factors impact and how it's not a simple question of the singular increase in temperature. We applied that to the entire country again, using those first-order approximations. Again, we find that rutting is more concentrated in the northern regions of the U.S. and less so in the southern regions where it's already quite warm. To wrap up, the message and the takeaway here is climate stationarity and the loss of that stationarity. What kind of impacts might that have? Well, it seems obvious that increases in temperature of the level projected to occur from these models will impact pavement performance. How does that manifest in the real world? whether that manifests as a loss of longevity, increased maintenance actions, or other sources is a little bit more difficult to say. What we do see is that, and most importantly, is that structural configurations to account for these increases in temperature are probably going to be insufficient. This is a preliminary suggestion, meaning that material selection becomes even more important. And to bring this about more full circle to chrome rubber, identifying materials that are more resistant to temperature increases or less sensitive to temperature increases becomes a method to mitigate these potential impacts in the future. Mr. Chairman, I apologize I went over, but I do appreciate the time.